Hi all, so in today's video I would like to cover the Jacobian and change of variables. So the Jacobian and the change of variables is an integration technique that we have for multivariable calculus. It's an extension of the substitution rule that we had in single variable calculus, but it really takes full use of iterated integrals and how we can make our regions easier while also making our variables of integration easier, because often some variables will work better with certain certain functions will work better with certain coordinate systems, and changing between such coordinate systems is important. And the Jacobian is a generalized way that we can change between these coordinate systems, and we can use it to derive our area differentials for double integrals and our volume differentials for triple integrals. So let's get started, and this will be our last topic for unit, unit 4. This will be our last topic for unit 4. All right, let's get started. Let's think about the idea of a transformation first. The idea behind a transformation is taking some set, in our case an ordered pair or an ordered n tuple, of coordinates. So we take a coordinate from the u space into the v space. So you could have a coordinate system like this, and we have an image of our region. So we have an image of our region in the u1, u2 space, and that's our region R, and it looks something like that. And then we could transition that region using a transformation into maybe something that looks like that, a square, which is a lot nicer. We'll call that R prime, and this might be in the v1, v2 space. So the idea behind the change of variables in multivariable calculus is we're changing these regions from a nice region, or from an ugly region to a nice region. Perfect example of this is taking the integral of a function over a circle, right? If we did that in the Cartesian coordinates, that would not be fun, just because we would need to deal with all of those square roots. But we can transfer everything into polar coordinates, and then everything becomes easy. In fact, you can usually separate the integral over theta into just 2 pi, which is something that is very nice to be able to do. Anyways, if I have the integral of f of xy dx dy, then that can easily be transferred into an integral of f of r cosine theta and r sine theta, r dr d theta. But there's obviously a geometric argument of why we can get from dx dy to r dr d theta as our differential, but we want to, I wanted to wait until we could find a generalized way to do that. That's exactly what we're going to have here with the Jacobian. So we will consider transformations such that x can be modeled as a function of u and v, and y can be modeled as a function of u and v. So u and v are our new variables, and we would be wanting to change something from the xy space and into the uv space, so that we can change from an ugly shape in the xy space to a nice shape in the uv space. That would be easier for us to integrate. So for a double integral, what I want to consider is I want to consider the case of a square in the uv space, right? So let's consider a region in the uv space that is a square, or a rectangle, and it has dimensions of delta u by delta v, right? And we will start at some u naught v naught, right? And we would have these lines would be modeled by the equation v equals v naught, and of course here would be modeled by the equation u equals u naught, right? So the image that we have of our region in the xy plane might be something that looks a little bit different. That might be modeled by some sort of vector function, right? So if I have the xy space that looks something more like that, so that's what our region looks like in the xy space, then I might have a function here, a vector function r, and r would be between the origin and wherever on this line, and that would be a function of u naught and v, right? And then this would be my x naught, y naught. Why is that my y naught? Because why not? That was a bad joke. And then here, we would have r with v naught and u, or u naught, or u and v naught, right? So now what I want to consider is I want to consider the tangent vector that we would have here. So the tangent vector, if I have r of u and v could be modeled by g and h. If g is a function of u and v and h is a function of u and v, kind of as we modeled earlier, that's of course x of uv and y of uv. Now, if I want to take the partial derivative of r, then I'm going to get partial u of g and partial u of h, but we defined g and h as being x and y, so we get partial u of x and partial u of y. We can do the same for this guy here and get dv of r. So now what we have is that we have a nice differential section that we have, right? So now what we can do is we can reformulate this as a equation with using the definition of the partial derivative. So what we will do is we will consider the vectors that that sweep out this this area, this vector, and then that vector. And of course, what we will get is we will get r sub u. We'll get r sub u, or partial r with respect to u, is going to be the limit as delta u approaches 0 of r of u naught plus delta u and v, and v naught, sorry. And then that's going to be minus r of u naught and v naught. And that's all over delta u, right? Now what we can do is we can manipulate this equation a little bit and multiply both sides by delta u. So then we have r sub u, partial u, delta u, right? So that looks fairly nice for us. And it means that we can approximate the region R as a parallelogram determined by the vectors of the partial derivative of u for R times the quantity delta u. So we can use this because we have a differential direction and then we have a magnitude of delta u that we can approximate our area with. We can do the same for v, and then what we get is we get this here. And what we can do is we can take a cross product. The cross product, the magnitude of the cross product, gives an area, if we remember back from earlier. That would give the area of this parallelogram. Now you can see where this is going. What we do is we shrink these vectors, or these deltas, down to d's, and then we get infinitesimal cross products. So what we're going to do is we're going to say that the area is equal to the magnitude of the cross product between the partial derivative with respect to u of r and the partial derivative with respect to v of r, and then we tack on du dv, okay? So now what we can do, what we're in the position to do, is we can take our cross product, and the cross product ends up being a determinant of a matrix. Now, what we know about a cross product is you can take the cross product as a determinant of a matrix, and we already kind of covered that in the last unit, so I'm not going to go through it again. But anyways, what you end up getting is you get times k hat, and then this is times the last unit vector k hat in the z direction. Anyways, you get that as your magnitude, so if you take the magnitude, then you can get rid of the k hat. So you get the determinant of all of these partial derivatives, and we call this partial of xy over partial of uv. And there's another name for this. We call this j, and this is the Jacobian value. So what we have learned now is we have derived the quantity for the Jacobian. Now the idea here is what we do now is we take this into consideration when we do an integral. So what our integral now becomes, if I want to take the integral over a new region, the integral over s prime maybe, I can take this as a function of u and v, considering I'm starting from x and y, and then this is times the Jacobian times our differential du dv. So that's how we can transfer from an xy integral into a uv integral. And we use the Jacobian, and the Jacobian produces some sort of constant, and that allows us to determine what our new differential is. Now what's interesting is that what we're going to do in the next video is we're going to derive this for polar coordinates. You get the Jacobian as being r. So if you get the Jacobian as being r, then j du dv equals j will become r, and then du becomes dr, and v becomes d theta. This is a little preview of what's to come. Anyways, that was kind of a long-winded, maybe a slightly confusing definition for the Jacobian and the change of variables. Doing some examples is going to help out, and we'll cover that in the next video. Thanks for watching. We'll see you then.